What's going on, fellas? Doing a quick little experiment for Basil. We have a copper anode in place inside this electrolyte bath that came from our Ewaste refining process. This is Ewaste copper, and because the Ewaste anodes or Dewar bars are so dirty, getting pure copper can't always be done in the first run. So this is the second run. We are plating copper off of this 95% pure copper anode, and that will give us the 4/9 copper on these two cathodes here. I've just started the machine. The electrolyte is very cold. We are at we want 2.4 amps, and at this temperature that's giving me 0.7 volts. Okay, so here we are. After doing the whole cell test, we've determined that an effective amperage is going to be right around 3.2 amps based on the 16 square inches of surface area that we have. I've painted the back side of these cathodes with electric spray paint, and we have an anode bag over the anode. I'm trying to also observe the effects of the PCR testing I'm doing. PCR is a known method of reducing these nodules that you see, and it involves periodic current reversal. That's basically the acronym. Okay guys, what we're observing here is a periodic current reversal phase where I have converted the cathode into the anode, and we can actually see cation flows tethering off of the crystal ends like streamers from lightning rods on a building. So if we think about the reverse analogy of this, when we are plating metal, these little crystals act like little antennas or lightning rods, and they consolidate this cation flow and accumulate it, I guess if you will, into these points, causing a cascade effect where the crystals and the lumps get even worse and worse because of that streamer antenna effect. But those cation flows are a pretty amazing thing. They're very fast. This is real time, and you can see they've got a pretty good velocity to them. Okay, so I got some very strange crystals going here all of a sudden. Man, those things are reflective, shiny. That was right after the periodic current reversal. So I think the iron may be starting to come out. Look how freaking shiny those are. Look at that. You guys see that? You can actually see the cations traveling off of those crystal nodes. I want to get one last look at this because I got to turn my back on it for a while. Wow, is that getting crystally? Look at that. That is like glittering. Very clear. Okay, fellas, so here is a quick sample array of some of what happened. First of all, we have the pure copper anode that we use for the baseline test. You can see that dissolved up quite a bit. You'll notice there is zero anode sludge, no discoloration whatsoever in this felt. This felt is clean. There's nothing there. Maybe just a slight amount of browning there. Okay, now here is the e-waste anode. A lot dirtier of a material. You can see there is some brown staining there. I tried to remove as much of this stuff as possible. It's caked in there pretty good. There is no anode sludge per se. Just some minute discoloring or discoloration. You can see here it pretty much ate itself apart. And before I jump off of this, I want to make note of something. Notice how our anode is completely dissolved away. That is also the reason why we see these irregularities in the plate. You have to have a perfect anode surface area. The morphology and the topology have to be consistent, or else you get inconsistent plating. This is a known fact. Why is one plate different than the other? These cathodes were both connected to the same electric charge. The distance was as close as could possibly be, not down to the millimeter certainly. But if you'll notice, our e-waste anode is not the same on both sides. We have a smooth side, which I wish I would have taken note, and we are in the next test, and we have a rough side. I would propose that this plate here, this cathode, was exposed to the smooth side of our anode, and that this cathode was exposed to the rough side. I may have folded this in such a way that both sides were smooth, and I think I did. So that could be completely mute. It appears I did do that, but it's hard to tell with so much gunk on here at this point. I'll double check in the video. We'll be able to see later on. But for the purpose of contrast, here is some straight up e-waste anode. Look at what the anode bag looks like from that process. There is no copper filings like this. It's all powdery dirt. Even the small pieces of copper have a lot of lead on them. Very powdery, dirty material. So you've got e-waste anode coming over to the e-waste cathode, which produced this right here. So this should be one step more pure than that article there. And there is a lot of glittering in here. And a lot of this inconsistency came from the fact that our anode had dissolved on us. So I ran the test a little bit too long, basically, and it caused inconsistencies in the morphology of the anode, which have reflected. And I think what happens is you start pulling so much copper out of solution. That's another cause for these crystal formations, I believe. I also did not have any leveler or hydrochloric acid or anything like that in the solution. This is what happens when you have a high iron contamination or just a lot of other contaminants. This is e-waste cathode that came from a very dirty solution, so we will need to treat that solution as the process is going. We have two pure copper cathodes, and the reason we're doing that is because the smoothness of the cathode is very important. You can see here these cathodes are very rough. That is also said to cause these irregularities in the topology. The crystal grain structure changes and everything. So we're going to try that and see how important is it. In addition to that, we are also going to use a pure copper anode to see if we get any of this kind of funny stuff here, which also indicates that we have a high tin content. There's this brassy appearance to the copper. They say a brassy appearance is indicative of that particular contamination. I am going to paint the back of these cathodes because I only want the front surface area to be active, because it kind of messes up my surface area calculations doing it the other way. If we allow the back to also react as we did here, because it doesn't react as strongly, so all different types of changes take place in the back region there. So after we do that, we're going to make another solution. We will make up a new solution and run the test again using all pure copper to see if what we are interpreting as contamination is in fact contamination. If we get this same effect again, it's just going to be, oh, well, Bob, you just don't know what the hell you're doing. It won't mean that the contamination's really high. I propose we're not going to see this same thing happen, though. In this test, we're doing a whole cell test, which is where we are reading the electrolyte solution to determine the most effective current density. You can't just pick a current density based on specifications you might find in a book somewhere because of all the different variables. So in the beginning of this test, we're starting off at 0.1 amps, 0.3 volts. Okay, I accidentally left it in for 18 minutes, but no biggie. I got a timer set. I wanted to get a look at it before oxidation takes over. We've got a real clean salmon color at 0.1 amps. 15 minutes on that piece. Not much of a difference at all. We're going up to 0.3 amps now. Okay, so here's a quick look at 15 minutes at 0.3 amps. They do oxidize up a little bit after they dry, so I wanted to get a look at it as soon as we're done. Okay, here's 0.8, 0.9 amps. I decided to change the spectrum up a little bit, apparently. Okay, out of this amperage, we're getting powder. This is too high. I don't like the way this 0.1 and 0.2 is looking, if anything. As you get on down the line, it just gets kind of drastic. Straight up powdered metal. So, we're going to take this information into consideration. As you'll notice, we did not get any crystal growth, though, per se. So it's a clean solution with no iron in it. Okay, so it's 10 hours later. We have been running this piece for 10 hours. No crystal growth. I just tried to do the bend test on this wire, and this stuff is stiffer than regular copper. Regular copper wire is. I know how stiff a piece of copper wire is, and it should be easier to bend than this stuff. Oh man. Okay, so here's with the pure copper. About a half hour in. Camera's not picking it up very well, but the dang thing's got some good shine to it. Look at that. Man, the camera's just not capturing the quality of this. Here are some other variations of the same 0.2 amps. So you can see 0.2 amps, 0.2 amps per square inch can give you all these different effects depending on the temperature of the bath or the additives in the bath, the contaminations. So that bath seems to be okay. We're not getting anything like this right here. This is the high iron contamination stuff right here. This piece actually looks really nice. There we go. That's kind of a good look at the shine that I'm seeing. It's got a real nice shine to it. Got some current lines going there. Maybe this is the back. We'll have to take. Okay, so this is 2.5 hours. Those little nodules are common. You just can't see them on the large sheets because they're so small. But this copper has a Very beautiful appearance. Very clean. This is at 0.2 amps per square inch. So now what we're going to do is the next part of the test. We're going to take these two copper cathodes and an anode wrapped up in some felt, and we're going to reproduce this test here to see if we get the same kind of mess. All right, I'm back to 3.2 amps. I've heard some very wise people say that starting off with a low amperage is good. So I turned it back up, and we are starting to get that same shiny pattern that we've seen on our test piece. Now the camera isn't picking it up the way I can see it, but we're getting some shine there, dude. Look at that. The camera almost wants to get it. Okay, so the lights are messing up on me, but here's the plate. It looks like it's in really good shape. You can see the stark difference as far as the crystal growth situation. I'm going to put these in some dilute hydrochloric acid, so we got a chance to get a look at them tomorrow also.